friends, welcome to the channel Physics by IITians. In this video, we will learn how to solve questions of molecular spectroscopy, and the questions are discussed that has already came in previous GATE papers. So let's start the video. So the first question. The first question is, which one of the following gases of diatomic molecules is Raman, infrared and NMR active? The options are hydrogen, carbon monoxide, HCl and O2. So we have to find out this diatomic molecules which one is Raman, infrared and NMR active. So we have to know what is the Raman active or what is the criteria of a molecule to be Raman active, what are the criteria for the molecule to be infrared active and what is NMR active. So let's get to the details. Now the IR spectroscopy, that is the infrared active, okay, because the vibrational spectroscopy or IR spectroscopy, this the vibrational energy levels gives you the IR spectra or the spectra which lies in the infrared region. What are the vibrational modes? Molecules have different vibrational modes. They are, if they are in at equilibrium, or there are some bending modes, there are some stretching modes, there are some asymmetric stretching modes, and due to this different stretching, bending, symmetric stretching, asymmetric stretching, they have different energy levels and they occupy different energy levels, and if that energy levels you excite that energy levels, you get spectrum lies within the IR region. And for the vibrational spectroscopy or IR spectra, we have to have a molecule that is that has a change in the dipole moment. That is, there can be the change in the permanent dipole moment due to its vibrational motion, or there can be a change in the induced dipole moment due to the vibrational motion, and the oscillating dipole will give you the radiation or the spectra. That is the physics. We have already discussed it in our vibrational spectroscopy lecture. Now we have to find out which one is the dipole moment, there is dipole moment or induced dipole moment. Now for hydrogen, there is homonuclear molecule, so there is no dipole moment or no change in induced dipole moment. This oxygen also the same case, and CO also there is there are some of the modes can be vibrational active, infrared active, or some of the modes cannot. And HCl also, there are some of the modes can be infrared active or vibrational active, some of the modes cannot. So it can, we can consider B or C option. A and D just cancel. Now Raman is for the case of the scattering of the molecules when the scattering is inelastic scattering. So whenever suppose a laser light is incident on this molecule, this is the molecular configuration, and here we get the scattered light, one as same with the incident light frequency and another is different from the incident frequency or incident wavelength of the electromagnetic radiation, and this scattered light where lambda varies from the incident lambda, this is called the Raman scattering. And for the Raman scattering we need the change in the polarization. We don't need any permanent dipole moment or we don't need any change in the induced dipole moment, rather we want a change in the polarization, and these two options can also be Raman active for certain modes. Now we will find out the NMR criteria, that is nuclear magnetic resonance. Now suppose we are taking nuclear magnetic resonance means we have to deal with nucleus. So suppose we are taking a spin half nucleus, okay. Now these nuclei are electrically charged because there are protons, and many have spin that causes them to behave like a magnet. So whenever you are applying an external field, external magnetic field, then these energy states can get splitted and atoms can have the splitting of energy levels due to its magnetic spin or this magnetic spin resonance, and the atoms of the plus half and minus half will lead to the different energy levels. So the spin with negative half, that is aligned against the applied magnetic field, and the spin with positive half, it will align with the applied magnetic field. and this kind of splitting, that is in the presence of the external magnetic field, this is called the NMR. Now this one we have to find out which nuclei is the odd number of nuclei. So here C12O16 is the even number of nuclei, so we cannot get spin half nucleus. Okay, and here this option C, that is H1Cl5, this is the correct option because it can give you Raman infrared NMR active NMR active spectra or NMR spectra. So the criteria for the Raman infrared and NMR active spectra, we understand it deeply. We need a spin half particle or odd integral of spin for the for the molecule to be NMR active. Now come to the next question, that is the expression for the second overtone frequency in the vibrational absorption spectra of a diatomic molecule in terms of the harmonic frequency omega e and anharmonicity constant xc is. So you have to find out what is the second overtone frequency or what is the expression for it in the vibrational absorption spectrum of a diatomic molecule, where the harmonic frequency is omega e and anharmonicity constant is xc. In this video also we will tell the about the vibrational spectra, and also we have also done the IR spectroscopy or vibrational spectroscopy video separately. I will give you the link. The fundamental band is the vibrational state, that is from V equals to 0 to V equals to 1, and we have to apply this energy of the vibration, this energy expression, that is EV equals to V plus half omega e minus xc to V plus half whole square omega e. Now for V equals to 0 to V equals to 1, this is called the fundamental band, where we get the energy expression for E V equals to 1 as 3 by 2 omega e minus 9 by 4 xc omega e, and V equals to 0 we get E as half omega e minus 1 by 4 omega e xc, and you have to take the difference between the two to get the fundamental band. So delta E will be omega e, that is this minus this, minus 2 into omega e xc. So this one. So 9 by 4 omega xc omega e minus 1 by 4 xc omega e will give you 2 omega e xc, and 3 by 2 omega e minus half omega e will give you the omega e value. So we get this fundamental band as omega e minus 2 omega e xc. Similarly, we get the first overtone band with giving the difference or calculating the difference between E V equals to 2 minus E energy of the vibrational level at V equals to 0. So it will give that 5 by 2 minus half omega e minus 25 by 4 minus 1 by 4 omega e xc, that is 2 omega e minus 6 omega e xc. The second overtone band will occur for the transition between energy levels, vibrational energy levels of V equals to 3 to V equals to 0, and after calculating we get the value as 3 omega e minus 12 omega e xc. So all you have to do, we have to put the value of V in this energy expression, and you have to calculate the energy difference between the two level, and that energy difference will give you that spectra. Okay, so the second overtone frequency that is occurring from V equals to 2 to V equals to 0 level will give you this at absorption spectra, that expression for the absorption spectra, that is 3 omega e minus 12 omega e xc. Here 3 omega e minus 12 omega e xc. Now come to the next question. The excitation wavelength of laser in a Raman effect experiment is 546 nanometer. If the Stokes line is observed at 552 nanometer, then the wave number of the anti-Stokes line is how much? So there is a Raman experiment, and the excitation wavelength, that is lambda nu naught, is 546 nanometer, and the Stokes line observed at 552, and you have to find out in which number, wave number, or what is the wave number for the anti-Stokes line. So the Raman displacement here, look, it is the Raman displacement, the spectra will look like this. The for middle one will be the relay line, that is the unscattered line, that is the scattered line with the same frequency, and here this is the anti-Stokes line, and this in the left it is the Stokes line. Okay, so the separation we can find out that delta nu between the two lines are the same, and this separation is exactly equal to this separation, that is delta nu bar equals to nu naught minus nu s. Nu naught is for the unchanged frequency line and nu s for the Stokes line will be equal to nu anti-Stokes line minus nu relay line. Okay, that is nu naught. So 1 by, in terms of lambda, we can write as 1 by lambda naught minus 1 by lambda s. It is written as 1 by lambda naught. It is written as 1 by lambda s equals to 1 by lambda as minus 1 by lambda naught. So 1 by lambda as, that is the anti-Stokes wavelength, is 2 by lambda naught minus 1 by lambda s. So lambda as can be calculated as lambda naught lambda s divided by 2 lambda s minus lambda naught. Now given lambda naught equals to 546 nanometer and lambda is equals to 552 nanometer. So lambda as can be calculated from putting this value, that is 540.12 into 10 to the power minus 7 centimeter. Now you have to find out the wave number, because we measure not in terms of frequency or wavelength, but in terms of wave number. So for wave number, it can be written as lambda nu as bar equals to, or nu anti-Stokes wave number equals to 1 by lambda as, that is 18514 centimeter inverse. So here in this question you have been asked that find out the wave number of the anti-Stokes line, and we get the wave number as 18514 centimeter inverse. The next question, the spacing between the vibrational energy levels in CO molecule is found to be 8.44 into 10 to the power minus 2 electron volt. Given that the reduced mass of CO is 1.14 into 10 to the power minus 26 kg, Planck's constant is 6.626 into 10 to the power minus 34 joule second, and 1 electron volt equals to 1.6 into 10 to the power minus 19 joule. The force constant of the bond in CO molecule is how much? These questions look very difficult, but actually these are very easy questions. So come to this question and understand what to do to find out the force constant of the bond in the CO molecule. Now given as the energy difference, look here, this is the given data, that is the spacing between the vibrational energy levels of the CO molecule, that is delta E, and this delta E for the vibrational levels. So delta E equals to 8.44 into 10 to the power minus 2 electron volt, and reduced mass has been given as 1.14 into 10 to the power minus 26 kg. You have to find out the force constant of the bond in CO molecule. So we have to apply the quantum mechanical harmonic oscillator energy, that is vibrational energy, that is E equals to h nu into n plus half, where n starts from 0, 1, 2. Okay, so frequency of the oscillation here, nu is 1 by 2 pi root over k by mu, where k is the spring constant or force constant and mu is the reduced mass. So why we are considering this one? Because we consider that atoms or molecules, when they are vibrating, they are actually a spring mass system, and this spring, due to this spring mass system, they certain time they can stretch, they can get asymmetric stage, they can get distorted. So these are the vibrational motion, and the linear harmonic oscillator you can assume. And also for the real molecules we have to assume the anharmonic oscillators, not the harmonic oscillators. All this has been discussed in previous IR spectroscopy video. So here in this case we have to find out the force constant of the bond in CO molecule. So the force constant we can write that E equals to, from the data, first we have to calculate the vibrational energy level difference, that is delta E. Now E equals to h nu into n plus half. So n equals to 0, 1, 2. So for n equals to 0, it will become h nu into half, and for n equals to 1, it will become h nu into 1 plus half. That is delta E equals to h nu. That is the energy difference assuming the ideal harmonic oscillator. And delta E has been given as 8.44 into 10 to the power minus 2 electron volt. Now delta E can be written as h into nu. So h into 1 by 2 pi root over k by mu. So delta E becomes h by 2 pi into root over k by mu. Now delta E has been given, h value has been given, mu value, that is reduced mass value, has been given. What we have to find? The k value, that is the force constant of the CO bond. So you find it, that is k equals to 2 pi by h into delta E whole square into mu. So 2 into pi, that is 3.14, divided by h, that is 6.626 into 10 to the power minus 34, into delta E as 8.44 into 10 to the power minus 2, into, that was in terms of the electron volt, so we have to write it in terms of joule. So into 1.6 into 10 to the power minus 19 whole square into mu, that is 1.14 into 10 to the power minus 26. What we get? That is 187 Newton per meter. The answer is 187 Newton per meter. So look how much easy the question is, but looks so difficult, right? So don't afraid of atomic molecular questions. These are actually very easy, and don't mug up also. You have to understand why we are doing this, because we are assuming the harmonic oscillating vibration of that molecules, of that atoms inside the molecules. That's why we are taking this harmonic oscillator energy levels, and these are all quantum harmonic oscillators in case of atoms or molecules. So we apply that formula. Okay. Next question is the equilibrium vibrational frequency for an oscillator is observed at 2990 centimeter inverse. The ratio of the frequencies corresponding to the first and fundamental spectral lines is 1.96. Considering the oscillator to be anharmonic, the anharmonicity constant is. Now, in the earlier question, we assume that harmonic oscillator. This here, the question has been mentioned as anharmonic oscillator. So we have to apply the anharmonic oscillator formula and its energy level formulas. And the thing that is given, the information, the ratio of the frequencies corresponding to the first and fundamental spectral lines is 9.16. So the V equals to 0 to V equals to 1 is our first fundamental band, and the first overtone is V equals to 0 to V equals to 2, and we have calculated the fundamental band value, that is energy difference delta E equals to omega E minus 2 omega E xc, and for the first overtone the energy difference is 2 omega E minus 6 omega E xc, and the ratio between the fundamental and the first overtone has been given as 1.96. So 2 omega E minus 6 omega E xc divided by omega E minus 2 omega E xc equals to 1.96, and we have to find out the anharmonicity constant, that is xc. So calculate this, that is 1 minus 3 xc divided by 1 minus 2 xc will be 0.98. So xc is 0.019, or you can write as 0.02. So option 2 is matching. The next question, match the typical spectroscopic regions specified in group 1 with the corresponding type of transitions in group 2. So there are specific region, and here there are specific transitions. We have to match which one is going to match with the right group, that is the group 2. So the infrared region belongs to the vibrational transitions of molecules. So P belongs to 3. The ultraviolet region belongs to the transitions, that is the first one, that is P equals to 3, and the ultraviolet region belongs to the electronic level transition, because electronic spectra lies within ultraviolet or visible region. And third one is the X-ray region. It belongs to the transitions involving the inertial electrons. Okay, so this one is for vibrational, this one is the X-ray region, and gamma ray region is the nuclear transitions. So P equals to 3 First of all, look here the option. The first option P equals to 3. You can only, if you know the infrared region lies in the vibrational transition of molecules, you can eliminate all the other options. So, but we should know each and everything. So P equals to 3 is the vibrational transition of the molecule. Q equals to Q matches with 1, that is this one ultraviolet region, that is sure, that is electronic transitions, and R matches with 4, that is the extra region with the transition involving inertial electrons, and S matches with 2, that is the gamma ray region matches with the nuclear transitions. Okay, so option C is the correct option. And now the next question, this is another question that came in GATE 2012. The information was given that the first stroke line of the Raman spectrum lies at the 6B separation, and that 6B was given as 6B equals to 12.96 centimeter inverse. You have to find out the rotational constant, that is B. So for 6B equals to 12.96 centimeter inverse, so B will be 2.16 centimeter inverse. That is the rotational constant. And if somehow they don't tell you what is the find out the rotational constant, but they tell you find out the moment of inertia of that particular bond. So you have to apply that B first, find out B, and then B equals to H cross by 4 pi IC, and you find out the value of I from that, that is from B, information of B. Or you are asked to find out the intermolecular interatomic distance, that is R naught. So then you have to apply I equals to mu R naught square. So B can be written as H cross divided by 4 pi mu R naught square C. So there are a lot more possibility of questions. So here the first separation between the Stokes or anti-Stokes lines from the Raman line is 6B, and then these lines will be separated with the separation of 4B, that is the consecutive separation between the Stokes lines or anti-Stokes lines. Okay, so here we have understand how to solve the molecular questions and the molecular spectroscopy questions, question from vibrational, question from Raman's, or questions from NMR or nuclear magnetic resonance spectroscopy. Hope you understand, and you surely you can join our test series, and the test series link will be activated from 16th of August, and this link will be activated, and you can give at any time, you can give the test, but we request you to give the test within 5 days, so that you can get your rank compared to the other participants. So full length test or topic wise test, or full length or topic wise, you choose according to your scheme. The cost has been minimum, kept minimum for your benefit. So only with the 700 rupees you can attempt 15 tests, and you can attempt lot more practice tests before your exam. So hurry up, and don't forget to share it, and don't forget to like this video. And we have crossed 2k subscribers within 4 months, so we are so grateful to you, and thank you all our friends and students, that we shall cross many more milestones, and we shall continue to boost up your scientific mind through physics. Please join our Telegram channel, Physics by IITians, where we post daily quiz questions and other relevant research topics. So thank you.